So welcome everyone to this third session of 5-day FDP on energy engineering. Today we have with us in this session Dr. VSKV Harish. Dr. Harish is working as an assistant professor in the Department of Electrical Engineering at Pandit Deen Dayal Petroleum University, Gandhinagar. He has completed his ME with gold medal in power engineering from Jadavpur University in 2012 and PhD from IIT Roorkee in February 2017, both with MHRD fellowship. After his PhD, he worked as a postdoctorate fellow at TERI School of Advanced Studies, New Delhi, under Netherlands government-sponsored project on smart grid for rural India. He has been nominated for the prestigious Young Energy Research Award in 2016 and in 2018 at World Sustainable Energy Days, Austria. He was awarded Best Paper Award at Springer and IEEE National Conference in October 2019. He was granted international travel support by DST in 2014 and 2018 and by Soft Computing Research Society in India in 2017. He has published several research papers in journals and conferences of international repute. He has published book chapters with CRC Press, Taylor and Francis, and Springer, with an elsewhere book on green building to be published by 2021. He is also a member in various societies and institutions like ASHARE, IEEE, SCRS, CIBSE, etc. His research interests includes building energy systems and power system analysis. With this, I would request Dr. Harish to please take over this session and enlighten us with the concept of energy efficient buildings. Sir.
Thank you, sir. Thank you so very much. Can I start sharing my screen, sir?
Sure, sir. Sure.
Just a second. Is my screen visible?
Yes, sir. It is visible.
Very good afternoon, all of you. Thank you very much, sir, for your introduction. Thank you to the Department of Electrical and Electronics, GLB ITM, for giving me an opportunity to interact with all of you. They were back-to-back meetings, so hence hence the delay for my session. So straight away, we will be focusing on the modeling and control aspect with a reference to building energy efficiency for the next couple of hours. So the major focus will be on identifying buildings as an energy responsive entity with occupants' comfort and energy performance as primary indices. We will look into the basic background of or motivation of why buildings has been chosen for this topic, and among the buildings, inside the buildings, what are the services, what are the energy related or the energy intensive services that are responsible for the electricity consumption majorly inside the building. Then we will also touch upon the major small difference between energy efficient building and a green building. And then we will also look into how the concept of modeling and control, which is driven by the occupancy, is a participant inside the smart grid concept or the smart grid entity. Then we will brief around. My major focus will be on the research that I have been working on for the last 5 to 6 years, that is grid interactive building energy systems. And then we can discuss on the future scope. Also, there is one request I have with all the participants, that with due permission of the honorable coordinator for this program, if you have any doubts or any queries or any points you want to raise during the course of the presentation, I would request you to interrupt me then and there, and I would be more than happy to address any of the issues or doubts or any of the queries or any of the points you want to make, or you feel that it can be addressed upon. So you feel free to interrupt me, and we can have a point of discussion over then and there as well. Looking towards the energy scenario for buildings, Buildings as a service sector has been responsible for more than 33% of the total energy consumption and more than 23 to 25% to the GHG emissions. The graph which you are seeing on your screen shows the changes in floor area, population, energy, that is the building sector energy use, and the total GHG emissions. See, the total GHG emissions here focus on both the direct GHG emissions and the indirect GHG emissions. Sorry. The direct GHG emissions and the indirect GHG emissions. Direct GHG emissions are those emissions which are contributed and controlled by the entity under the process, under the study. That means, for example, we are riding a motorbike, right? And we are emitting gases to the environment, which comes under the greenhouse gas category. So we are contributing directly to the greenhouse gas emission. The other aspect is the indirect GHG emissions. Indirect GHG emissions are those emissions which are a consequence of the activities that have been carried out by the entity or the organization in itself. For example, we want to build up a green energy power plant or a solar PV power plant. For example, one of the world's largest single point solar PV power plant is the Kamuti power plant, which was developed by Adani in Tamil Nadu. Right now, there's a large infrastructure and equipment that needs to be brought from the manufacturer site up till the site of implementation or deployment. Now you can use different modes of transportation. Now those modes of transportation are majorly fossil fuel dependent. So during the building up or the construction of that power plant, you are indirectly contributing to the GHG emission by using that mode of transportation, which is emitting greenhouse gases. Both these direct and indirect emissions have been taken into consideration in the study which you are showing, which you are seeing. Now this red solid line which you can see, this shows for the changes in percentage for the last 1 decade. This has been derived from the International Energy Agency report of 2019. 2020 report has also come out, and the trends resemble this similar thing. So I have used this old report only. Now if you will see, this red solid line represent the changes in floor area, whereas this mustard line represents the changes in population. Now the population has been growing worldwide, but if you would see that the changes in floor area, the growth has been enormous. Now this is due to increased urbanization, increased standard of living, and of course increase in population. Also, the floor area which has been taken into consideration for the study does not only account for the horizontal floor area, but also the vertical floor area, right? That means the skyscrapers or the high-rise buildings which have been coming up, because as for each and every floor that you go for expansion, you increase your level of electricity consumption because you increase the implementation of the electrical equipment, majorly air conditioners, lighting systems. And also, as the high-rise buildings come up, you require motors that would lift up water up to an appropriate level and as and when desired, right? So both these things have been taken into consideration. Also, if we look into the Indian statistic, Indian building energy statistic, we can see that as a service sector, it is responsible for 33% of the total energy demand in India, right? Now, this is second most contributor as compared to that of industries. Also, inside the buildings, if you will see, we can see here that residential and commercial together are responsible for more than 30% of the total energy demand, and the others is 67%. Now, this again becomes an open-ended research topic, that in India, the categorical classification of the energy demand or the energy consumption based on electricity or non-electrical energy consumption holds true, right? Because the data is not available, or they have to be looked upon, they have to be analyzed upon, they have to be processed upon. So large number of researchers are also working on categorizing this. Why it is important? Because only then the researchers will come to know that where do we have good amount of potential to improve the energy performance of any building, be it residential or be it commercial. There can be institutional, municipal, so on and so forth, right? So this is again one of the open-ended topic that one can work upon. Also, if you will see the Indian statistic only, taking the 2017 as the calculated demand, electricity demand in terawatt hour per year, that is the annual electricity demand, it has been forecasted that there will be an exponential growth of electricity demand in buildings in India. Now, these are accounting for all these statistics, all the categories of the buildings. All the categories of the buildings have been taken into consideration for the studies which we are seeing. Now, we know that why this is happening. This is happening again, the same aspect that the urbanization in India is resulting to increase of towns and cities along with the rising population. Urban population, if you will see in India, it was reported according to some 33-34%, according to the World Bank collection of development indicators in 2018. Yes. And the increasing population in urban areas requires more buildings to work, live and interact, leading to an increase in number of buildings, further resulting to projected rise in the electricity demand. Right? So also in India, the buildings as a service sector is contributing to about around 1/3 of the total energy production in the country, right? And that's what we saw here in this pie chart. Inside the buildings, what are the major services which account for, which demand the electricity, which we can see here on your screen? For residential buildings, if you will see, coolers, fans, lights, air conditioners account for more than 50% of the total electricity consumption in residential buildings. Coming to the commercial buildings, the HVAC standing for heating, ventilation and air conditioning system, along with lighting system, account for more than 70%, 75% of the total electricity consumption in commercial buildings. That means if you can see that here, for an Indian typical Indian building, that can be residential or commercial, the building space conditioning that can happen through HVAC system for commercial buildings, fans, coolers and air conditioners for residential buildings, and the lighting systems in both residential and commercial buildings are accounting for more than 50% of the total electricity consumption by end use in any of the type of the buildings. It can be any buildings of any functionality, right? Now, if we come back to the global sector again and see the final energy use in the global sector, we can see here that electricity is one of the major contributor for the final energy use for the last 1 decade. Also, there is one point to be noted here that this again is coming from the International Energy Agency report. The biomass traditional has been taken differently as compared to the renewables here. This is because that the biomass traditional which has been referred to here is referring to the conventional solid biomass, that is the charcoal and forest or agricultural resources, which are being used in inefficient heating and cooking equipment. Renewables, on the other hand, have been shown differently here because they include the solar thermal technologies, renewable technologies, as well as modern biomass, that is wood pellets for heating and biogases. Now, if you see by end use, here final energy use is in EJ. EJ here stands for exajoules. EJ here standing for exajoule. 1 exajoule is equal to 10 to the power of 18 joules, right? Because this is a global figure. Now, if you see from the final end use again, this is again the global sector. According to Indian scenario only, the space heating and cooling according to clubbing both becomes a space conditioning and lighting systems are accounting for the electricity consumption inside a building. This is again the global figure. Yes, LEDs, large number of energy conservation and energy efficient measures have already been put into place. So, for example, CFLs were energy efficient. Now LEDs are being talked about as energy efficient, that is the light emitting diodes. So they continue to be important in reducing the energy consumption for lighting. But as the floor area, as we saw in the previous graphs, that the floor area, the increase of floor area has been so much, that the growth has been so much, that this is dominating. This is dominating the effect that is been coming from the light emitting diode or the implementation of LEDs, right? Now again, this air pollutant or the indoor air quality has become important, especially post pandemic scenario, after this pandemic scenario. Why? Because of course we all even the media talks a lot about outdoor air pollution, right? Or the air quality index outdoor. And we as an occupant always, even when we have air conditioners, people or the inhabitants who are living in metro cities like Delhi, Kolkata, Chennai, Mumbai, they go for air purifiers, external air purifiers, and they install it inside their homes. Now the air conditioning companies or the manufacturers are working together with the standardizing agencies to work on a concept where then external air purifier inside the building space is not necessary, right? That means that the mass flow rate of the air conditioner unit is in such a way that it is allowing the fresh air to come inside the building space, circulate according to the volumetric space, and then move out depending upon the occupancy and the nature of activity of the occupant as well. Now, why this is being worked upon? Because the chances of virus transmission, that is the SARS-CoV-2 transmission, the chances of virus transmission inside the building space should be as less as possible, right? Now, that's why it is also important that whenever we talk about the building energy efficiency or anything, the health or the indoor air quality, maybe the CO2 concentration in parts per million inside the building space need to be taken into consideration. Why? And I will demonstrate the output of my research also, and why we have taken that is because the sensors are available. Because when we work on modeling and validation, we work on the taking the data and it accumulate the data, have a data acquisition system, and then process it through laptops or computers. So the sensors are available for the same as well. Now, if we look into the forecasting demand, we have seen that the PM 2.5 is one of the scenario that has to be taken into consideration when we talk about the buildings as a sector. Now, what are the building energy systems? See, building energy systems, we define the building energy systems as the systems which are responsible for the energy consumption or usage inside a building. Now, this can be any physical equipment or machinery or a process or a combination of them. That means they are comprehensively used to provide the comfort to the inhabitants of the buildings. That can be thermal comfort, visual comfort, acoustic comfort, indoor air quality to the occupants. And the major services delivered by the building energy systems, providing thermo-visual comfort to the occupant, thereby maintaining a very healthy indoor air quality for good productivity of the occupants, right? Now, what we have analyzed so far, what we have realized so far, we have realized that buildings as a sector, is responsible for more than 1/3 of the total energy usage and also contributing to 26% of the GHG emissions. That means it has given a good potential for energy reduction and also for the GHG reduction. Second point, inside the buildings, the HVAC systems and lighting systems are the major equipment or the machinery which are responsible for the energy consumption inside the building space, right? Now, looking further, let us now look into the green building aspect and see how the energy efficient building comes inside that green building aspect. Now, several definitions are available for green buildings. Again, I would urge the participants not to just, that's what I share with all my students as well, is to go through legit, genuine reports that are available free source online on our ministry's website and also the intergovernmental websites, and just not follow Quora or Google or Wikipedia, right? Now, if you talk about green buildings, several definitions are available, exist for the green buildings, but taking that into consideration, the famous one or the standardized one are coming from the United States Green Building Council, the WGBC, and the United States Environmental Protection Agency. The US Green Building Council states that it's a holistic concept that will take into account all the activities that would have a positive or a negative effect on the natural environment as well as the people who are inhabiting the buildings every day. Whereas the World Green Building Council states that all the activities that have been taken into consideration from the design part or the design phase up till the operation, and how much negative impact on the climate and the natural environment is being minimized, and how much amount of positive impact is being there, we can quantify it and regard or deem a building as a green building. The United States EPA widens this definition and states that not only from the design but even from the siting part, the amount of resources that are being used from the siting part during the design, construction, operation, maintenance, renovation, and up till the deconstruction, then we regard all the activities taken into consideration will be accounting for if the building is green or not. Here, deconstruction is nothing but we call it as a selective dismantlement of the building component. This can be for some retrofitting, some recycling, some repurposing, or waste management, or some reusage, right? If you see these three definitions of the green buildings, it's nothing novel. It's not a new thing. It is nothing but what we call it as optimal usage of Jal, Vayu, Prithvi, and Akash. Simple. Optimal usage of Jal, water, Vayu, air, Prithvi, soil, Akash, sky. Right? And how much we are exploiting it, and how much of the passive design we are talking about, and what are the activities and how much amount of resources being exploited during those activities will be quantified through the rating system, and then an appropriate organization will rate that particular building as green or not, right? Now, if we talk about the green building rating is nothing but a mathematical tool that will evaluate the performance of a building and its impact on the environment. It is just very much similar to what we do with our students. We grade their performances, we rate their performance in terms of absolute marks, and then depending upon the marking mechanism or grading mechanism, we grade them. Similarly, we quantify the usage of any particular building, taking some benchmark scenario, and then we compare that scenario and calculate how much green that particular building is. So any rating system will consist of a predefined set of criteria that will relate to design, construction, and operation. Means all the things that were outlined in the definitions. Right? In India, there are predominantly four, rating systems. USGBC's lead here stands for Leadership in Energy and Environmental Design. There is a rating system from IGBC standing for Indian Green Building Council. Then we have very famous GRIHA, which was developed by TERI, adopted by MNRE. It is the Green Rating for Integrated Habitat Assessment. And then we have the GEM rating from ASSOCHAM. ASSOCHAM stands for the Associated Chambers of Commerce and Industry of India. Right? Now let us, also, because we would talk about the energy efficient buildings and the modeling and control part, it is important to know that there are two other prescribed guidelines One is the Energy Consumption Building Code, ECBC, and the another one is NBC, which is the National Building Code. They provide the guidelines on the energy consumption, and all buildings in India need to comply with these prescribed guidelines. If you talk about this ECBC, which is the Energy Consumption Building Code, what happened was, with an view to of increasing electricity demand and the need of managing it, an effort of energy conservation was initiated by the government of India, where the Energy Conservation Act was formulated in the Gazette of India in October 2001, right? And through it, the Bureau of Energy Efficiency in 2002 was instituted to implement this act. So, and the ECBC first was formulated in 2007, and the user guide was available in 2009, somewhere in July, I think. And it provided all the the technical guidance, which our buildings will be what do I say, qualify for that ECBC. And this development of act and also the development of ECBC code led to the amendment and adoption of the code at the state level also, because India being the subtropical regions, there are different climatic variation, aesthetic usage of the buildings, and there are a large number of factors, very dynamic in nature. Because an energy efficient building in Kolkata may not be an energy efficient building in Mumbai, and an energy efficient building in Mumbai may not be an energy efficient building in Chennai, right? So the amendments are being made according to the local weather conditions also. So we had an amendment in 2010 as well, and also the commercial ECBC. The commercial ECBC was amendment, I think, in 2017-18. 17-18. It mandated that any building, any commercial building falling in the purview of connected load greater than equal to 100 kilowatt, or the contracted demand greater than 120 kVA, will need to comply through this ECBC, right? And also, with the existence of current policy landscape, the process of erecting the ECBC compliant building is still not very much clear among the owner or developers of buildings. And then there were again some rules which were published in 2018 again, right? Not only commercial ECBC, we also have the residential ECBC, which is very famously called as Eco Samhita. Eco Samhita. All of the documents are available on the Ministry of Power or the Bureau of Energy Efficiency website. Yes, there was some draft industrial ECBC in 2019 as well. Because there are set to increase the number of urban buildings, and they will be covered by ECBC if mandated, potentially increasing the overall impact on the energy savings, at least at the city level. So also coming to the smart cities level. So this was about all the ratings in India. Again, one of the famous is this Griha rating. If you would see here, it's again a tool which was developed by the TERI, the Energy and Resources Institute, adopted by MNRE. It was famous because it has very good salient features, which one of them was, it was a performance based rating, because it was designed for different climatic zones, because it incorporated the regional variations as well. It unified multiple national and state level codes. A few codes I have told you, that is ECBC, NBC. Apart from that, also the CPCB, that the Central Pollution Control Board, and CGWB, that is the Central Groundwater Board, into a simple set of criteria as well. It places good emphasis on the concept of the integrated design approach and implementation of cost-effective strategies. It also ensures the comfort which is necessary, the acoustic, thermal, and visual comfort for all the occupants of the buildings as well. Now, having looked into that aspect, whenever we talk about green buildings, the three major points that need to be looked upon, are, first, of course, is the energy usage, the electricity form usage, and the not electrical energy usage. Second thing is the waste disposal. How much amount of waste is being how much amount of waste is being created during the construction, during the operation, and also if there is any selective dismantlement of that building, and how much efficiently you are using the water as well. So you talk about water efficiency, energy efficiency, and the waste disposal whenever you speak of the green building. Whenever we come to the energy efficient buildings, our major focus is on the energy efficiency aspect, or the energy part aspect. So this is the major difference between the green buildings and the energy efficient buildings. There are other differences, also very minute differences as well. Now, if we talk about how we can, the concept of this modeling and control, and through the grid interactive building energy system, where I talked about that it will be, the buildings will be acted like a responsive energy entity in the power system, especially from the consumption side, through the smart grid scenario. This is the graphic that I have taken from the National Buildings Institute, which developed a report in 2020, that is the Grid Optimal Buildings Initiative. The New Buildings Institute, sorry, not the National Buildings Institute, but the New Buildings Institute. They outlined that the role of buildings, be it of any nature, it can be an office building, a residential building, or an industrial building, along with their energy storage and renewable energy in the utility industry, is changing. And this graphic which you are seeing on the screen is showing how the buildings can play an important role in, catalyzing this transformation of buildings in the electrical power grid. See, what happens is the building occupants expect a reliable, high quality electricity of demand, and they are not bothered about what is happening behind the meter. Like if I am the occupant and I am paying the bills to the distribution utility, or the distribution company is giving me the bills, if I am using a switch, and if I'm wanting to use any equipment, if I'm switching on the switch, that equipment should work, boss. So that is the contract I have with the distribution utility. I am not, as an occupant, I am not bothered right now where that electricity is coming from, what's the grid dynamics, so on and so forth, right? But if we talk about as the buildings, when a large number of net zero energy buildings are being worked upon, on-site renewable energy is being worked upon, energy efficient practices are being worked upon, the electric vehicle charging infrastructure is coming up. So it will always need to be built upon. It cannot be always be like petrol pumps, that you go through a charging station, it's like a petrol pump. They're working on some high-rise buildings, they have their own dedicated EV charging stations. So they need to be built upon to that particular buildings or that particular community. So the role of the buildings as an entity, as a nodal, is changing in the grid. So it can become as a consumer and also as a producer of electricity. That is the supplier of electricity when and wherever the time of need comes. So it has to have a control strategy in such a way that it is not jeopardizing the behavior or the dynamics of the electrical power grid. It should support the any building should support the should support the grid in such a way that it is able to provide, the grid is able to provide high quality and reliable supply of electricity. So the New Buildings Institute came up with a term. They coined a new term for a building which they said as grid citizen. Grid citizenship. Grid citizen is nothing but a building with a good grid citizen. Sorry, a good grid citizen is a building that will contribute to reliable, safe, and affordable operation of the electrical power. Right? Right now, there are no metrics in use today that can define this building level grid citizenship. There is no metric. right now. There is no standard right now, but the concept is very very interesting to work on the grid interactive building energy systems. Because and also the current thinking on the topic is still fragmented, and different players are using different language, different numerics to discuss the topic from a variety of perspective, not only from the technological sides and also from the governmental political sides, and also from the policy side as well. As we know that electricity in India is a concurrent subject, so it is a politically influenced subject as well. So what are the things that are required to develop grid interactive building energy systems? The very first step is the building energy control modeling. That is the building energy modeling and also the building energy control modeling. See, what happens is, in almost all control projects, we have studied control engineering, instrumentation and control as well. We need to develop good models, good precise models, and then only we can develop any control strategies to work upon it. So that means we have, even in buildings, even for the buildings, we develop building energy control systems that would enable any equipment or any appliance to operate in such a way, in a controlled manner, as and when desired, according to the objective of the building owner or building manager. That objective can be to provide maximum comfort, or the objective can be to provide maximum energy efficiency. Now for this you require data to be worked upon, and because you need to develop good precise models also. So you have building automation systems or building monitoring systems through sensor networks and through data acquisition systems. They take the data, process the data, and they give it to the building energy control systems. Also, whenever we talk about how do we need to do, for example, it can be a situation where a building at certain periods of time need to operate in such a way that it needs to provide maximum comfort, and other periods of time it needs to operate in an energy efficient manner. So for that we require a very good aspect of building energy management system, the building energy management system. All these things, a mathematical model for a building energy system is necessary, because we need to design and tune the controllers, and we need to simulate their performance as well, right? The second step is the modeling of the grid interaction with the building energy systems. How do we model the integration part of the building energy system through the grid, through the power system dynamic scenario? There is two aspects of it. One can be of power electronic scenario, where we work on the converters, the control of converters, the power quality aspect, and the other is the power system dynamics aspect, as when to know that we can use an economic load dispatch problem, where the buildings can act upon as a storage maybe, and they can help in the voltage support and the frequency support of the electrical power grid. Also, it is important to work upon the occupancy participation as well. So what happened was, I will be discussing one my personal experience with all of you. What happened was, we visited one of the agencies where we worked upon our postdoctoral project in Netherlands in February 2020, and it was one of the beautiful buildings. It was an energy efficient building. It had a very good design. It was fully automated. Even the doors, windows, even the air conditioners, it didn't have the buttons. It had a control strategy during which, depending upon the occupancy, the lift would come and the doors would open and close. The principal investigator of our project, she's a professor and clean energy enthusiast. So she never uses motorbikes. She uses bicycles also, and she never uses lifts or elevators. She climbs through the stairs as well. So she wanted to go to her office. She was getting late for the meeting, so she climbed up the four floors. Her office is on the fourth floor. Went inside her room. She wanted to cool off, but her air conditioner was set in such a way that the thermostat was set in such a way that it was not cooling the building space. Because it was February, it was already cool. It was taking the consideration of the outdoor weather data, and also the occupancy pattern. Because what happens is, whenever we talk about the smart sensing systems or the smart control systems, we design one particular building aspect, and for the same site and the same design, we change the building functionality. For example, if I have mathematically virtual model, if I have developed a one room according to the site and according to the building materials, each and everything, and I want to calculate the heating, ventilation, and air conditioning load, then that would depend upon the functionality of that building particular room as well. If the same room is being used as a library, my thermostat set point control system would be different. And if that same particular room at the same location is being used as a gym, then my metabolism would differ, and the thermostat set point setting for the air conditioner would differ. Right? So that is the aspect that was taken into consideration. So hence it is necessary and important that even when you talk about this energy efficient building design, or during the operation, the retrofit analysis, the occupancy comfort needs to be taken into consideration inside your models as well. And also the control strategy should be developed in such a way that in the future aspect, in the future use for the next 10 coming 10 years as well, it needs to provide a certain space where other strategies can be put into place, in maybe in parallel with the already existing strategies. So that would be step 3. Step 4 would be, how would you implement it? What are the physical challenges that would be there wherever you implement the grid interactive building energy systems? How do you evaluate it if whatever I have been speaking about for the last 1 hour is true or not? And how to do the fault detection and diagnosis part. The step 4 has not been done from our side, because we are working on the research projects for research funding for the step 4. Now, when we talk about the building energy modeling as step 1, it is nothing but a mathematical model that would describe the behavior of the building energy system under consideration. The modeling the modeling structure of a building energy system consists of 3 building blocks. One is input variables, one is the building energy systems itself, and one is the output variables. The process of modeling this building energy system involves determining any one of the building blocks when adequate information about the other 2 are already available. Right? The input variables which you are seeing here are called as regressor or forcing variables, which are the building block of the modeling system that acts on the building energy system. These variables can be, internal or causal heat gains, thermostat set point settings, so on and so forth, which can be controlled by the systems engineer, will be controllable, which cannot be controlled by the designer. The control system designer will be regarded as uncontrollable. Depending upon different research papers, these are also modeled as disturbances, and the state space formulation differs. Simple. The building energy system is nothing but for which the parameters or the equations which we use to describe the behavior of the system which you are taking into consideration. For example, in my research, as I have already outlined, we will be taking into consideration the HVAC, heating, ventilation, air conditioning system, and the lighting system. And then the output variables. Output variables means what do you want from the model? आप अपने model से चाहते क्या हो कि model को जब simulate करेंगे, what will be the output of it? Will be the total energy consumption be output, or the timely power be the output, or is there any cost involved? Will that be the output? Is any occupancy behavior of how they are using the lighting system or HVAC system be the output, or is there any design output, that the design of window, for if you are designing window like this for that particular room, this is how the energy consumption is. If you design the window in any other way, that is how the energy consumption is. You work on the W to W ratio, that is window to wall ratio, so on and so forth. Now, depending upon this process, building energy models are classified into 3 types of models. The very first one is a white box model. White box models are pure theoretical models. Each and every information about the subsystem, equipment, and process that is happening inside that building space or the building energy system under study, we know about it. We formulate all these equations. We use either analytical formulations or the numerical methods, or artificial intelligence methods to solve those problems, and we get the outputs. So we know the inputs, we know the building energy system. Such models are called white box models. Such models are very accurate models. They are the benchmark in accuracy, but they demand a large amount of computational power because of large number of equations that need to be solved. Second type of models are called as black box models. As you can see on your screen, black box models means you don't have any information or adequate sufficient information about the building energy system under study. You give certain inputs, you get the outputs, you use some input output relationship, regression analysis, or numerical methods to develop input output relationship, and that input output relationship in mathematical form becomes the modeling equation or the characteristic equation of the building energy model. Such models, black box models, are simple in nature. They are very good with computational efficiency, but they suffer from accuracy. Gray box models, on the other hand, are a combination of white box and black box models because they are inherited from the white box models and also called as semi-physical models, right? They are semi-physical models because they are inherited from the white box models, which are also called as the physical models. And the parameters of these models are defined by the system through parameter identification techniques. Just like we have studied throughout our machines, that each and every machine, be it a transformer or a rotating machine, always has an equivalent circuit. Op-amp has an equivalent circuit. A BJT amplifier has an equivalent circuit. A multi-stage Darlington amplifier has an equivalent circuit, right? And each and every equivalent circuit is composed of dependent, independent sources and the resistor, capacitor, inductor networks. Where very famously we talk about the single line diagrams, we talk about the pi models of the transmission line, so on and so forth. Now we know that. But what should be the value of the parameters that are defining that particular equivalent circuit model? That is parameter identification technique. So you develop certain parameter identification techniques in order to identify the parameters of the modeling structure which is already known to you, right? Now, it's the building energy. There are certain softwares which are available to develop the model and to operate the model, simulate the models, building energy models. Such programs are called as building energy simulation programs. Very famous one are the Energy Plus, eQuest, ESPR, Transys, and DOE's software. Again, for particular applicability, where do you want to know or what is the purpose or the main motivation of developing that building energy model will drive your decision of using which energy simulation software you want to use. For example, I developed the model through equations and then convert into transfer equations and then state space equations in MATLAB, and validated it through intra-model validation comparison through Energy Plus. Same set of inputs, same model in Energy Plus, compared both the outputs. Also compared this with already published articles, the outputs coming from the already published articles, and then that's how the validation happened, right? So not only the empirical validation, but the intra-model comparison validation also happened like this. So the building energy simulation programs, for my purpose, because I had that purpose, I used it Energy Plus. Depending upon different purpose which you want to use for, you can use different energy simulation programs, which you are seeing on your screen. Now, after knowing what are the different types of energy models, what are the softwares available for the development of energy models, what are the parameters that need to be taken into consideration as significant parameters for modeling our building energy system. So these are the set of parameters. The nature, again, the controllable means that behavior of that particular parameter can be controlled or changed through a certain control strategy which will be developed by the designer, right? Whereas uncontrollable is the nature of such parameters where the behavior of that parameter cannot be changed and beyond the control of the control system designer. R here stands for residential and NR here stands for non-residential. Now I have one question to the participants. here in the list of the parameters that I have outlined, there is one or few parameters which I have regarded as uncontrollable, but can be controllable when you talk about the building energy modeling or building energy control systems. There are one or few more than one parameters which I have regarded as uncontrollable here, but can be actually controlled. Can anyone care to or venture a guess here? Anybody? There is one or few parameters which I have regarded as uncontrollable but can be actually be controllable. हेलो, हाँ मैडम लेक्चर में मैं करता हूँ फोन आपको 1-1.5 घंटे बाद. नहीं मैं आ गया, नेट नहीं चल रहा था तो मैं आ गया. ठीक है, थैंक यू. See, if you will see here, or in a particular room which you are sitting and watching this webinar or witnessing this seminar, you will see that geometrically you are sitting in a cuboid, right? Now you have 6 faces, you have different walls. Few of the walls would be, depending upon your construction, few of the walls would be dedicated to the outdoor exposed to the outdoor weather conditions. Few and for the indoor weather conditions, there can be partitions as well. And you may also have windows, right? Now, if I have suitable curtains and blinds, I can control how much solar radiation is coming inside the building space, right? If I can mathematically analyze and detect at what particular period of time the curtains are being closed upon, how much they are being closed upon for the opaque elements and the glazing, and look upon how much amount of outdoor air temperature or solar radiation is directly getting transmitted inside the building space, not through the walls but through the window elements, then that can be a controllable parameter. Right? So this is what my MTech student right now is working upon. We are working on some probabilistic nature of that particular parameter and trying to incorporate that behavior inside the modeling and seeing how we can get a different patterns and what are the errors for already published results. So that is one thing here. Again, for building energy modeling and simulation, there are certain key technical terms that are important or necessary. See, energy modeling is nothing but development of computer models of building energy systems, right? Simulation is the process of using that computer model to build a virtual replica and run that model and operate that model, right? And for developing that building energy models and using any of the software, these are the key technical terms that all of us should know. The very first is the construction and layers. See, for building simulation, each type of building section is termed as one construction. For example, one particular wall, I gave you an example that you are geometrically sitting inside a cuboid with 6 faces. One of the faces can be one construction. In that one construction, there can be different layers. For example, your wall can be made up of brick. Then you have cementing. Then you have putty. Then you have a wallpaper inside, depending upon your luxury. So each and every layer has a thermophysical property, right? So this is important for you to know. And then the equipment sizing. See, besides calculating the cooling load, the simulation programs are also equipped with the capability to calculate the sizing of that particular equipment. For example, if you are calculating the lighting load, you have to calculate how much number of lighting auxiliaries or lighting fixtures you require, right? Because that would again have a costing effect. Kyunki cost effect hoga. Then you have to work on the cost benefit analysis and then again the payback period. Similarly, for HVAC systems, the heating, ventilation, air conditioning systems as well. Hourly simulation. See, energy's use is simulated in a building for every hour of the simulation period. For this purpose, hourly weather data is required, and the simulation engine of that particular building energy simulation program has to have the capability of handling the load calculations on an hourly basis and account for any effect of storage that can happen. In order to do that, you require an input file. Input file is nothing but the description of the buildings that will be in a form that can be understood by the simulation program. This input file usually consists of building usage schedule. This usually consists of the building usage schedules. What are the schedules that are being used upon this input file? The geometry of the building, the orientation of the building, all the constructional details, and the usage of the building and the functionality of the building. As I told you, if the building is being used as a gym or as a library, completely different functionality for the same particular form. Then we have an output file. Now, this program which you are using may generate more than one output file, and as I told you, depending upon what is your purpose of developing that building energy model, your output file will be there. Then you will doing or performing the sensitivity analysis. This is nothing but the process of optimizing the energy performance of a building by running different scenarios. By running different scenarios, or several scenarios can be worked upon. Different scenarios can be worked upon, as I was giving you an example of window to wall ratio, changing different window to wall ratio and calculating the total energy usage and through the HVAC system or the heating load. Then we also have a schedule, which is nothing but the hourly usage pattern of any zone or any equipment. The simulation engine, which is nothing but heart of the program. For example, when you develop any MATLAB programs, you have different simulation engines, you have different solvers which you can develop, which you can use inside that particular software, and in order to achieve better results at a lesser period of time. Then you have something called as thermal zone. You can have a building space, for example, which would have a centralized air conditioner, or which could have a different air conditioning zone. So for that, for example, if you have a building where you have a few classrooms, inside that building there is one room where you are housing your all the servers, and that should be conditioned at a much lower temperature. So that will be of different particular zone, and your classroom can be of different particular zone. Then you have visualization, 2D models or 3D models, how you want to visualize it, how much daylight is coming in, each and everything comes under the visualization. Then we have weather file, which contains the hourly information about that particular site or location under consideration: wind speed, wind direction, rainfall, atmospheric pressure, cloud cover, solar radiation, solar temperature, so on and so forth. Now let me give you some example how it happens. See, energy auditors are being appointed. They do some sample output. For example, for a particular building under consideration that they have been worked upon or they have been called upon, and they develop plots or graphs like this. Using this, they break down how much amount of energy is being used by each and every service, right? From this particular example, it can be seen that from this total energy consumption, 38% of the energy consumption, this is annual, aggregated annual 38% is being done through cooling. That means the air conditioners are being used for 38% of the time for the cooling structure, right? Now, if we break down this cooling structure, we can break down that the window solar load is contributing to about 35% of this cooling load. So you can work upon different possible solutions. It will always be a multi-objective solutions. It will be multi-criteria decision making, because if you say you are getting this very good energy efficient practice, see, we know when we go to the market, we not only get 5-star air conditioners, TVs or refrigerators, we also get 2-star air conditioners, TVs and refrigerators, right? So it's a multi-criteria, the thing, where your energy performance will be lesser, so the cost will also be lesser. Now here in our study for the grid interactive building energy systems, we develop building energy models through thermoelectrical analogy. This is very much similar, as I told you, that for each and every equipment that we study in our electrical engineering, we have equivalent circuits. Equivalent circuits usually are RLC networks, right? Similarly, every thermal equipment will also have an electrical equivalent circuit. This is because of the analogy that is being used, that heat flows from a higher temperature region to a lower temperature region through a particular medium. Similarly, electricity or current flows through a higher potential point to a lower potential point. That's why the temperature in thermal engineering can be mapped as voltage in electrical engineering. Heat flow rate Q dot can be mapped as electrical current. Heat capacity in joules per kilogram Kelvin is mapped as thermal capacitance in degree Celsius per meter cube. Conductivity in watt per meter Kelvin is mapped as resistive conductivity in mho. A temperature gradient dou capital T by dou small x is mapped as voltage gradient, which is dou capital V by dou small x. The rate of temperature rise is mapped as dou capital T by dou small t as rate of voltage rise, which is dou capital V by dou small t. Here, another one of the most important or significant research gap that we worked upon or we wanted to address was the building energy control designers, where large number of papers were published, were not bothered about the modeling aspect. They took only the single layer modeling, and researchers who were working on the modeling aspect were majorly doing the CFD analysis, and where they were not bothered about the computational power and what control strategies would be developed over here. In order to bridge that gap, we developed multi-layered building energy modeling, and for each and every construction element such as a wall or a window, we developed resistance capacitance networks, pi networks, and we cumulated those pi networks and developed a model for a single room. We formulated that model as a state space model because of the ease of analyzing it. Then we looked upon the performance characteristics, performance analysis for the rise time, settling time, maximum overshoot, steady state error for different step inputs as well, or the test inputs as well. So what we did is we developed this RC network for one building wall. So as I told you that you are sitting geometrically inside a cuboid, one of the face is this 3 resistance 2 capacitance network. Why we have taken this is because it's a second order model because we have 2 characteristic equation. If we apply KCL, Kirchhoff's current law, in this node Tx and this node Ty, I told you we are mapping this temperature as voltage and heat flow rate as current. So that's what you are seeing here as well, right? And through so we have 2 KCL equations, 2 Kirchhoff's current equations, 2 characteristic equations, which are ODE of the form which you are seeing here. Now, as I told you, we worked upon the gray box modeling aspect. That is, it is necessary to find out what is this value of R1, R2, R3, and what is this value of C1 and C2. Each and every wall and each and every construction element comes with a thermophysical property. Thermophysical property. It's a characteristic for each and every construction element. Thermophysical property. Such properties are the thickness of that particular layer, specific heat capacity of that particular layer in joule per kilogram Kelvin, thermal conductivity of that particular layer in watt per meter Kelvin, and the density of that particular layer in kilogram per meter cube. From the manufacturer, we get the data. From that data, we calculate or compute the total thermal resistance of that particular wall or construction element and total thermal capacitance. After calculating this total thermal resistance and total thermal capacitance, we then formulate these resistances and capacitances as some fraction of the total thermal resistance and the capacitance as some fraction of the total thermal capacitance. So now the problem becomes to find out the values of all x's and find out the values of all. So that means my unknown vector is nothing but an augmented vector of x and y, which is nothing but x1, x2, x3 augmented by y1, y2. Also I have to satisfy this property because these are certain fractions. The resistances, all the resistances and all the capacitances are fractions of the total thermal resistance and total thermal capacitance. That means x1 plus x2 plus x3 should be equal to 1 and y1 plus y2 should be equal to 1, right? How do we do that? We develop a non-linear time invariant constraint optimization technique in order to minimize the error between the benchmarked accurate white box model and the our gray box model. In order to do that, because we are working on the conditioned space. Conditioned space means I am saying that the geometrical description which I told you, that we are sitting inside a cuboid, that is being conditioned through an air conditioning system, the heating, ventilation and air conditioning system. So that is provided through a parameter of QHVAC, right? Which is nothing but can be, as I told you in the analogy, is modeled as electric current. Electric current. What should be this? Again, this is a time dependent parameter. So how to formulate it and how to simulate it? We develop a HVAC system model. We use Ashley Handbook of Fundamentals and use theoretical textbook equations to develop an all seasonal HVAC system. And conventional traditional technique is using the PID controller. So we already use the PID controller. So our traditional baseline scenario is PID controlled HVAC system. And as I told you that we are also worked upon the indoor air quality. So the number of air changes per hour, that is the air circulation, is also calculated through this. Again, these are again textbooks theoretical equations which have been formulated through Ashley Handbook of Fundamentals. As we all know, whenever we work on the transmission system, electrical power transmission system or distribution system, we use IEEE test bus systems or other test bus systems. Similarly, we used ASHRAE test cases where we developed an ASHRAE test building room. And these were the parameter values that you are seeing on your screen. Now, how did we get the values of all the resistances and capacitances? We developed a benchmark model for a particular wall like this. We formulated the thermal energy transfer through the partial differential equation through Newton's law of cooling. We formulated it as bifurcated it in mesh form, and then we solved it through a central difference scheme through Crank-Nicolson method, and we got the output for a set of a test input which was given to this numerical model. This numerical model we regarded as the most benchmark model in terms of accuracy. Then we started with that 3 resistance, 2 capacitance, that is the 3R2C model for a multi-layer wall. We started with the guess values of X's and Y's. We gave the same test input here. We got the output for the reduced. This is our target model for the reduced order target model. We then computed the sum squared error for these two models, and the objective function then became the minimization of this error function, subjected to the constraints and the boundaries which we already outlined here. Using this, we solved this by minimizing the gradient difference, and we got the values of x's, the augmented solution vector x1, x2, x3, y1, y2, multiplied it with the total thermal resistance, got the values of resistances and capacitances for each and every wall of the cuboid. This is what is this data table showing here. So this is the geometrical description of particular cuboid. This gets converted into a resistance capacitance network. For simplicity, every 3 resistance to capacitance network has been modeled as a box here. 3 resistance to capacitance network has a modeled as a box here. AW1 stands for adjacent wall 1. AW2 stands for adjacent wall 2. The orientation of north, west, east, south is given here. Yes, WIN here stands for windows. Because of the nature of the window, large amount of outdoor air, outdoor condition is transmitted inside the building space. So we modeled the window as a 2 resistance, 1 capacitance network. So a single order model. So this was our win 1. This was our win 2. This was C win. This was TBS. BS stands for building space, or that is the indoor air temperature. This is that node, and T here is the outdoor. Of course, again, this is conditioned by the air conditioning system. If it is not conditioned, that becomes zero, right? This parameter QHVAC becomes zero. Very simple. Now, the occupancy part. What we developed is, we know that we are taking into consideration the HVAC system and the lighting system. So we computed the comfort in terms of indoor air quality, in terms of visual comfort, indoor air quality, CO2, carbon dioxide concentration in parts per million, visual comfort in terms of lux levels, illumination inside the building space, and thermal comfort. We have not taken acoustic comfort into consideration. Thermal comfort, the building space air temperature, and the relative humidity of the building space, right? And so my one of the objective becomes maximization of the comfort inside that building space, and another objective becomes minimizing the comfort of that particular minimizing the energy consumption, minimizing the energy consumption or energy usage that is being created through that HVAC systems and the lighting systems. We developed a genetic algorithm, PSO based optimization algorithm for it. And any multi-objective optimization algorithm will not have a single solution, but there will be a Pareto front. That means that these are the solutions which are non-dominated. That means this will not affect the other solutions as well, and not go for a bad solution part. So because we worked on minimization problem, so we converted a comfort function as a discomfort function. 1 minus comfort function becomes a discomfort function, and any point above this was bad solution, and this was the region of no solution. And these are the sample pool of solutions here as per the Pareto front. Some of the sample solutions I have outlined here. You can see with the reduction in energy consumption, the comfort is also getting reduced, and for more energy consumption, the comfort is high, touching to the tune of 98 to 99% as well. Again, for the particular parameters of building space air temperature and CO2 concentration, for a particular averaged thermostat set point setting here, because of course we will not have a single thermostat set point setting, depending upon the occupancy behavior and also the outdoor weather condition. Throughout the day, you will change your AC remotes, you will change your set point setting for the AC. We took an averaged value. This is again one of the limitations of our work. If we have to make the thermostat set point again a time dependent function, so this particular optimization becomes a dynamic optimization problem. We are working on that also. So with PID controlled only and with not the multi-objective optimization control, this is the behavior which you are getting. And with the multi-objective optimization based control, or the building intelligent building energy control and comfort management strategy, these are the outputs which we are getting here as well. Similarly, for the CO2 concentration, for the illumination level or the lux level inside that building space under study, and the overall comfort occupants which you can see here. If we talk about the energy performance or energy savings, we can see that we are getting lesser energy savings, but I want to bring your kind attention to the development or the improvement of the overall occupants as well. So we are getting a win-win situation here, where we are getting the energy savings as well, and we are also achieving the good occupants comfort. That means we are moving towards an reduction in energy usage or betterment of energy savings without jeopardizing the comfort of the occupants for the building energy system taken into consideration. How do we now say that this would participate in the smart grid scenario? See, several definitions of smart grid exist. Just a second. Several definitions of smart grids exist, and several organizations are working on these definitions of smart grid as well. This is the National Institute of Standards and Technology, the United States conceptual model. This was outlined in 2010. Now it has been outlined again, amendment again in 2018, where it shows all the partners or players, how they are incorporated or formulated or participating in the smart grid scenario. Several definitions exist for the smart grid scenario. One definition comes from the ETIP. This is the European Technology Innovation Platform, which defines smart grid as the scenario where we can work. Oh, sorry. Am I audible, sir?
Yes, sir.
Okay. Sorry. Right. So there's one definition from ETIP, which is European Technology Innovation Platform, which underlines the concept of intelligent integration, sustainability, low cost, and security of electrical supply. Another definition is from the United States, not United States, from the International Energy Agency, which focuses on the use of ICT tools, coordinating and the efficiency of the system, and ensuring all of this is attained at good minimal cost and good stakeholders involvement. Then the International Electrotechnical Commission stresses the concept of flexibility and interactivity of the smart grid. They also stress the importance of optimization of the system operation and an efficient and economic supply. The European Commission, on the other hand, defines smart grids as energy networks which are having the capability of automatically monitoring the energy flows, and they can adjust to the changes in supply and demand. Ministry of Power, Government of India, through its National Smart Grid Mission, also defines smart grid as an electrical power grid that has the capability of automation, communication, and information technology systems to monitor the power flows, from the point of generation up till the point of consumption, up till the end use level. Right now, we monitor only up till the meter. Now they are also looking into that load monitoring aspect. So that means that the distribution utility will be able to monitor how much power is being used by your air conditioner, by your refrigerator, or by your any other systems which you have been given upon, right? So monitoring the power flow from the point of generation up till the point of the end usage. That is where our grid interaction of building energy systems comes, and control this power flow in such a way that you are able to match the generation and demand at all times of the day or near real time, right? So this is one of the basic definitions of smart grid. This is the basic definition of smart grid that has been outlined by the Ministry of Power through NSGM or National Smart Grid Mission. This is just one snapshot of the electricity sector in India. When we talk about renewable energy status, it's important to talk about it because a large number of rooftop solar PV is going on, which is being acted both in terms of building integrated photovoltaics and building adaptive photovoltaics. Rooftop comes under building adaptive photovoltaics, and whenever you have facades in your walls of the buildings, it comes under building integrated photovoltaics. Apart from this, you also have electric vehicle charging stations in your high-rise residential vicinity, which in itself is a solar-based DC charger for fast charger and solar-based AC charger for smart charging. So till July 2020, these are the scenarios. This is old one, new one has come up. So excuse me for this. I will change this and will send this new figures to all the to the honorable coordinator, and they can pass it to all the coordinators. Again, anything that you want to know about the information about the smart grids, I welcome you to go through the IEEE PES or IEEE Smart Grid website, and also through the International Smart Grids Action Network, anything which is legit as per the definition of smart grid and microgrid or virtual power plants or smart energy systems will be outlined here, right? Now, where can we see that our buildings would be participating in that? See, for every particular building, I told you we will develop the state space model, aggregate all the power levels, and we get the cluster of models, cluster of buildings. Then develop a distribution network strategy, develop a distribution network, and for each and every bus, we develop this grid dynamics through the swing equation. This equation holds valid for any bus where the generator is connected. If there is no generator connected, the LHS becomes 0. And the buildings as an accumulated power level participates through this parameter. The loading parameter. The number of buildings which are connected to the kth bus. Connected to the kth bus. And we can model this grid dynamics of the particular building energy system. Now for a grid interaction or a grid interactive building energy system, what are the physical equipment that are being required? This is one of the formulated scenario that or the design that I proposed, that it can, if we have a rooftop solar PV, that is a presumer, a particular building with an on-site renewable energy generation. We will have sensing and measurement in order to sense the load data for each and every building energy system taken into consideration. Also the storage, that can be a stationary storage battery, mobile storage like electric vehicles, and also the thermal energy storage systems. And through the optimization and control through the energy meter would be communicating through the distribution utility. This concept can also be formulated and expanded to the peer-to-peer power sharing scenario, where one particular building, be it a prosumer or a consumer. Prosumer is a building which consumes and produces its own energy. Consumer is just any building which does not have the capability of on-site renewable energy. Both these would act as a peer and have the capability of sharing their excess energy, sharing their excess power to the buildings in the vicinity, in the neighborhood, when and when it makes sense, or when and when it is desired. So it's a distributed power scenario. One of the architectural or one of the mathematical architecture that can be proposed is like this, where you have a centralized peer-to-peer station which would act as any other peer. Why we have taken this as an external, if you see few of the results, there is no centralized P2P and it is completely decentralized. But here why I'm showing this is because this is what we applied to our postdoctoral project, where we had it in Bake Bazar area of Gaya district in Bihar. So we were working on the developing and implementing smart grids for rural India. So the meters which we were installing need to be of low cost. So all the optimization algorithms or the major decision making was being done, decision developing strategies were being formulated in centralized P2P station, and the buying cost of electricity and selling cost of electricity at each and every hour of the day was communicated through this meter box. Through we had a router and we had an LED display. If you go to other reports or projects, they do it through GSM, and that is through mobile as well. But because we wanted to have it completely in a mobile aspect, we started it with, and costing was also one of the factors. So we started with an LED display which was attached to the router, which was installed at each and every part of it. So what will every household or a building have? We very much know, for a presumer, we would have loads, batteries, solar PV, meter through a breaker connected to the microgrid. One of the interesting part here is the consumer also will have a battery here. Why? Because we are working on the trading strategy based on the price of selling and buying of electricity, which is driven through the demand supply ratio calculation at each and every hour of the day. Now, whenever the demand is less and the supply is more, the consumer, when have a storage, will be encouraged to buy that electricity from that microgrid, because when the demand is less and the supply is more, the cost of buying electricity will be lesser and the cost of selling electricity will be more. So the consumer would try to buy that electricity if the storage is available, of course. Now at other times of the day, when the demand supply ratio is more, that is the cost of buying electricity is more, but the cost of selling cost of this when you want to buy that electricity which is costly in nature, because the selling price is also low, selling price is also more, that the consumer would try to see this as a good business scenario and sell that electricity when the demand supply ratio is more. So this is one of the business aspect of where the even a household or a building which does not have the economic capability or a rooftop in such a way that it has a good solar profile would participate in the green energy or the green power scenario as well through a sustainable business aspect, because it has a net profit as well. Also, it would have a good, very good power system dynamics as well, because it will always try to bridge the gap between demand and supply at each and every time cycle for which we are doing this into consideration. This is the sniffer diagram. Each and every supplier and will have a smart meter, will have a wallet attached to it. Each and every smart meter and wallet will have a particular address that will be saved in database management system. And each and every transaction that has been happened throughout the day will be saved in the centralized peer-to-peer station, that is the knowledge base. These are the loads which we have taken into consideration. These are the results. We worked on a 3 household aspect. We worked on different household aspects as well, but for 3 building aspect, I'm showing you the result here. This was our project, the developing and implementing smart grid for rural area. This is the DISCI project for peer-to-peer, and this we compared it with already formulated results which used majorly blockchain, blockchain and other scenarios. We didn't use blockchain. We worked on the normal optimization algorithms as well. What lies in the future, what I'm really interested upon is how much willing is the particular peer and the particular building manager or owner in order to participate in this grid interactive building energy system. What are the data that needs to be known so that I can forecast this behavior, forecast the weather, forecast the pricing mechanism as well, and what are the scalability issues. What would happen if there are 100 households which are participating in this peer-to-peer, and the next day there is an unplanned 10 household load getting below. So what are the load frequency control that need to be worked upon? Should I need to have a centralized storage system as a battery? If centralized storage system is a battery, what should be that centralized storage system? Who would bear that cost? So on and so forth. Also, the planning pricing strategy for different ownership structures. Who would be owner of this? If centralized peer-to-peer station will be the owner, what should be the planning structure? If each and every user, it's a community-based system, then what should be the structure? Can each and every microgrid in itself act as a peer? Because we worked on an off-grid scenario, but that was a grid-ready solution, so that whenever the grid comes into the picture, it can be taken from that asset can be taken by that particular distribution utility. Whatever I have been speaking about, what are the chances that it will fail? What is the contingency analysis that I need to be worked upon? So that is also very much important. So in future, what I'm trying to work upon is developing a mathematical tool that would evaluate the socio-techno-economic analysis of a prosumer-based energy systems and assess what will be the impact of particular buildings into the power system, that is the technical impact, and also on the aspect of the environmental impact of that particular building into consideration. These are the few research areas that we have in the Department of Electrical Engineering of PDPU Gandhinagar. We have renewable energy systems area, we have power systems operation control. These are the different research groups, and each and every research group is led by esteemed faculties of our department, which are majorly postdoc or PhDs from reputed institutes in India and abroad. We also have a good infrastructure for modeling and simulation laboratory. We are on the verge on acquiring Red Screen Homer as well. We are on the verge of it in order to create the complete energy scenario as Well, these are the softwares which are the legit licensed softwares which we have in our department. I welcome you all to go through the websites of PDPU. We have BTech Electrical Engineering program, MTech 2-year MTech Power Systems program. We provide stipends for both GATE and non-GATE scholars. We have 1 year full-time industrial internship also for our MTech dissertation, sorry, not internship, for a dissertation for our MTech program, which usually gets converted into placement scenarios as well. For PhD programs also, we have both GATE and non-GATE fellowships also, and we also provide the travel grants for scholars who want to present their papers in national and international conferences in India and abroad of repute. Thank you so very much for your patient listening. I really want to thank Professor Mohit Bansal sir for giving me an opportunity to interact with all of you, all the Department of Electrical and Electronics Engineering for GL Bajaj College, and also all the participants for your patient listening. I welcome you all. If you have any doubts or queries, you can ask me or you can email me if you want to have any point of discussion in future as well. Thank you so very much. Over to you, sir.
Thank you, Dr. Harish. Any of the participants you want to ask any question?
Good evening, sir. So I have a question regarding this energy efficient buildings, and myself Brajesh from Department of Electrical and Electronics Engineering, GL Bajaj. Sir, I have a query regarding piezoelectric based energy generation.
Okay.
Sir, it can be considered in energy efficient building, or it has some different area of research for electricity generation, and can it be included in the energy buildings?
You are working on the principle of piezoelectricity or on the aspect of it as system?
Sir, my perspective is like due to the pressure applied on the certain crystal, there is formation of voltage. That is the basic principle. So whether that principle can be integrated in this energy efficient or energy modeling buildings or not?
Sir, I think that can depend upon the level of wattage that is being produced by piezoelectric generator. I think it is very less. So I think it has to be stacked upon. It is just like a fuel cell, I suppose. So it has to be stacked upon, get to a level, and then if it can act as in the building energy efficiency, not on the design part, but if you can have a stack in such a way and do the cost optimization, that because it will work only as an isolation or an off-grid scenario, right? Because I don't have much of the knowledge of piezoelectricity, but I know that the power levels that of generation of piezoelectricity are less, sir.
Yes, sir.
Am I right or wrong, sir?
Yes, sir. Yes, sir. You're right.
So just like a fuel cell, it needs to be stacked upon. Stack karke, we have to series and parallel connection. That would take a lot of space.
Yes, sir. That will actually, the floor area can be covered with that thing. Then that idea can be implemented in the floor area of a building. Then that may include some or enhance some energy generation.
Okay. But for that, you would require a dedicated floor area, right?
Right, sir. Dedicated or on the stairs or on the floors. I mean, whether it can be implemented as energy efficient buildings or
See, sir, when if you talk about the energy efficient buildings, the on-site renewable energy needs to be cost optimal. So majorly solar PV is very famous for this. Apart from that, you need to have storage. Now lead acids are also going away, so you need to have good lithium based storages as well. Small winds are coming up, but small winds are very much beneficial or feasible economically also for high-rise buildings where we have clustered number of buildings, clustered number of households, where we have more than 400, 500 households, so on and so forth. In this scenario, I don't know, for piezoelectricity, what will be the energy density, power density of it per meter square, and then how do we work upon it? What is the cost optimization? I think that can be worked upon, the cost optimization, but right now there is no standard, sir. I don't think I cannot come across any standard or any document which talks about or mentions piezoelectricity, sir, in energy efficient.
Okay. Okay. Thank you, sir.
Any other question from the participants? Okay, I think all the questions are done. Thank you, Dr. Harish, for your intuitive lecture. And I hope and believe all of us have understood a lot about the energy efficiency and how can we increase the efficiency of our daily households. Thank you, sir. Thank you for your time. And we'll try to get in touch with you in future also.
Thank you, sir.
Thank you, sir. Thank you so much. Participants, the feedback link has already been shared with you. Kindly fill the feedback, and if you have any queries, you can also post it in the chat box.
हेलो 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 है उधर कुछ आवाज